Section: Introduction. In this section, we discuss large reasoning models, LRMs, like OpenAI and DeepSeek R1, which have achieved impressive results by enhancing reasoning capabilities through extensive reinforcement learning. Recently, both open-source and commercial entities have made significant strides in complex tasks, including Olympiad mathematics and competitive programming. The success of these LRMs is largely due to dedicating more computational resources to reasoning processes, leading to better performance in real-world applications. However, extending reasoning within traditional transformer architectures is difficult because of the quadratic complexity of the softmax attention mechanism. While various techniques have been proposed to address this, such as sparse and linear attention, most competitive LRMs still rely on traditional attention methods. The Hunyuan T1 model is an exception, but it is not open source and lacks detailed information. Our goal is to create and open source a large reasoning model that efficiently scales up computational resources and competes with leading models. We introduce MiniMax-M1, which features a hybrid mixture of experts architecture and lightning attention, a linear attention variant. MiniMax-M1 builds on our previous MiniMax-Text-O1 model, containing 456 billion parameters, 45.9 billion activations, and 32 experts. Our attention design incorporates softmax attention after every 7 blocks of lightning attention, allowing for efficient reasoning over hundreds of thousands of tokens. For instance, MiniMax-M1 uses less than half the computational resources of DeepSeek R1 for 64K tokens and about a quarter for 100K tokens, making it more efficient for both inference and large-scale training. Additionally, MiniMax-M1 supports a context length of up to 1 million tokens, significantly surpassing DeepSeek R1 and other open-weight LRMs. This capability makes it ideal for complex tasks requiring long input processing and extended reasoning. We pre-train MiniMax-Text-O1 on a large dataset and then fine-tune it to incorporate chain-of-thought patterns, laying a solid foundation for reinforcement learning. We introduce a new RL algorithm, CISPO, which stabilizes training by clipping important sampling weights, allowing us to use all tokens for gradient calculations. This method has shown to be more efficient than previous approaches. We also address challenges in scaling RL with our hybrid architecture, ensuring effective training. Our efficient RL framework allows us to complete a full run of MiniMax-M1 in 3 weeks using 512 GPUs, costing around $0.53 million. We curate a diverse set of problems for RL training, including both verifiable and unverifiable tasks. For verifiable problems, we include mathematical reasoning and competitive programming, along with diverse logical reasoning tasks generated through our SynLogic framework. We also create environments for complex software engineering problems, using execution-based rewards to enhance M1's performance. We train 2 versions of MiniMax-M1 with different maximum generation lengths, leading to MiniMax-M1 to 40K and MiniMax-M1 to 80K. The latter outperforms the former in complex tasks, showcasing the advantages of scaling computational resources. MiniMax-M1 surpasses previous leading models in various areas, particularly in software engineering and long context tasks, while achieving competitive results in other scenarios. To support collaboration and progress in the field, we have made our models publicly available on GitHub and Hugging Face, compatible with modern frameworks and equipped with deployment guides. This facilitates the integration of MiniMax-M1 into current inference systems. Section Summary. In this section, we introduce MiniMax-M1, a large reasoning model that utilizes a hybrid mixture of experts architecture and lightning attention to efficiently scale reasoning lengths and reduce computational costs during inference and training. Our model, which supports up to 1 million tokens and incorporates innovative reinforcement learning techniques, outperforms existing models in complex tasks while being open-sourced for community collaboration. Section: Preparation for Scalable RL, Continual Pre-Training and SFT. In this section, we focus on scaling up reinforcement learning to improve the reasoning abilities of MiniMax-Text-O1. To achieve scalable RL training, we first engage in continual pre-training of our base model to enhance its reasoning skills. Next, we implement a cold start supervised fine-tuning (SFT) phase to embed specific reasoning patterns into the model, laying a solid groundwork for the RL phase that follows. For continual pre-training, we aim to boost the reasoning and long context capabilities of our foundation model while ensuring diversity. We continue training the MiniMax-M1 model with an additional 7.5 trillion tokens, emphasizing high quality and varied data. We refine our methods for parsing web and PDF data and improve our cleaning rules to ensure we capture mathematical and code-related information effectively. We focus on extracting natural question-answer pairs from various sources, such as websites, forums, and textbooks, while avoiding synthetic data. We also perform semantic deduplication on the QA data to keep it diverse and unique. Additionally, we increase the share of STEM, code, book, and reasoning-related data to 70%, which significantly enhances the model's ability to tackle complex tasks without losing its general capabilities. In terms of our training approach, we reduce the coefficient of the MO auxiliary loss and modify our parallel training strategy to accommodate a larger training micro-batch size, which helps minimize the negative impact of the auxiliary loss on overall performance. We continue training MiniMax-M1 with a steady learning rate of 800,000 for 2.5 trillion tokens, followed by a decay schedule over 5 trillion tokens down to 8 millionths. For the long context extension, we have noticed that overly aggressive training length extensions can lead to sudden gradient explosions, complicating the optimization process. This issue arises because the earlier layers of our model do not adapt quickly enough to changes in the later layers. To address this, we implement a smoother extension of context length across 4 stages, starting from a context window of 32,000 tokens and ultimately reaching 1 million tokens. After continual pre-training, we proceed with supervised fine-tuning (SFT) to instill desired behaviors, such as reflection-based chain-of-thought reasoning, using high-quality examples. This creates a strong foundation for more efficient and stable RL in the next phase. We curate data samples with long chain-of-thought responses across various domains, including math, coding, STEM, writing, QA, and multi-turn chat, with math and coding samples making up about 60% of the total data. In terms of efficient RL scaling, we observe that the M1 architecture shows a clear advantage during inference, which supports the generation of longer responses. However, as we scale up RL with this hybrid architecture, we face unique challenges that can lead to instability or failure in the RL process. To tackle these issues, we develop targeted solutions that enable us to effectively scale up RL training for M1. We also introduce a new RL algorithm that enhances efficiency compared to existing methods, resulting in an efficient and scalable RL framework for training M1, which takes about 3 weeks on 512 H800 GPUs, costing approximately $0.53 million. We provide context on RL and present our novel RL algorithm, followed by a discussion of the specific challenges we encounter with the hybrid architecture and the solutions we implement to overcome them. For our new algorithm, CISPO, we denote questions from a dataset and define the policy model and response generated by the policy. We optimize the policy to maximize expected returns while applying a clipping operation to stabilize training. We find that the original clipping operation in PPO, GRPO negatively impacts training performance and hinders the development of long chain-of-thought reasoning behaviors. Through controlled studies, we identify that rare tokens associated with reflective behaviors are clipped out during updates, which is detrimental to learning. In response, we propose CISPO, which avoids dropping tokens while maintaining entropy within a reasonable range for stable exploration. Instead of clipping token updates, we clip the importance sampling weight to stabilize training. Our approach optimizes a specific objective that retains contributions from all tokens, especially in longer responses, proving effective in reducing variance and stabilizing RL training. We also introduce a unified formulation for CISPO that allows for hyperparameter tuning to control the conditions under which gradients from specific tokens may be dropped. We validate CISPO's effectiveness by comparing it with DAPO and GRPO in a 0RL training setting, demonstrating that CISPO significantly outperforms both methods with the same number of training steps, achieving superior training efficiency. Section Summary. In this section, we outline our approach to scaling reinforcement learning, RL, for the MiniMax-M1 model through continual pre-training and supervised fine-tuning, SFT, enhancing its reasoning capabilities with high-quality data while addressing challenges in training stability and efficiency. We introduce our novel CISPO algorithm, which improves RL performance by avoiding the clipping of important tokens, thereby stabilizing training and enabling effective long-context reasoning. Section. Efficient RL scaling with lightning attention, challenges and recipes. In this section, we highlight how our hybrid attention mechanism allows for more efficient reinforcement learning, RL, scaling compared to traditional designs, as rollout computation and latency are often the main challenges in RL training. As we conducted large-scale RL experiments with this new architecture, we faced specific challenges and created targeted solutions, which we outline below. First, we noticed a significant difference in the probabilities of rolled-out tokens between training and inference modes, which stemmed from a mismatch in computational precision. This issue hindered reward growth in our experiments. We found that this problem did not occur in smaller models with softmax attention. By analyzing layer by layer, we identified that high-magnitude activations in the output layer of the language model were the main source of error. To fix this, we increased the precision of the output head to 32-bit floating point, aligning the probabilities and improving their correlation from about 0.9 to 0.99. This stable correlation throughout training allowed for successful reward increases. Next, we used the ADAM-W optimizer, but we found that incorrect settings for the hyperparameters could lead to non-convergence. For example, using the default settings from Virl caused issues. We observed that the gradient magnitudes during training varied widely, with most being very small. To address this, we adjusted the hyperparameters to beta 1 equal to 0.9, beta 2 to 0.95, and epsilon to 1e15. We also discovered that complex prompts could lead to excessively long and repetitive responses, which threatened model stability. Instead of penalizing these repetitions, we aimed to stop them early. Since simple string matching was ineffective, we created a heuristic based on token probabilities. We found that when the model entered a repetitive cycle, the probability for each token increased significantly. Thus, we implemented a rule to halt generation if 3,000 consecutive tokens had probabilities above 0.99, successfully preventing instability and improving throughput. In terms of data and rewards for our RL stage, we integrated a variety of environments, including tasks that could be verified by rules and others that required reward models. We carefully designed a curriculum for these environments. For reasoning-intensive tasks verified by rules, we gathered a mathematical dataset consisting of hundreds of thousands of high-quality problems from public sources and competitions. We cleaned the data by removing incomplete samples and those with errors, ensuring no overlap with the supervised fine-tuning dataset. We also filtered out samples that could lead to random guessing and reformulated multiple-choice questions into open-ended formats. We used our internal model to extract answers and retained only those that could be correctly checked by our rule-based system, resulting in a dataset of nearly 50,000 high-quality mathematical samples. For logical reasoning, we selected 41 tasks requiring significant reasoning skills and synthesized data using our SYN logic framework. We set difficulty parameters to ensure a balance between challenge and learnability, generating about 53,000 logical reasoning samples. In competitive programming, we collected problems from online platforms and created test cases using our model. We filtered these problems based on quality and difficulty, resulting in 30,000 samples for RL training. For software engineering, we built verifiable environments using real-world data from GitHub, focusing on issues and pull requests related to common software challenges. We developed a sandbox environment to simulate realistic workflows, providing direct feedback on the correctness of our agents' interventions. This setup allowed us to curate several thousand high-quality samples, enabling our RL agent to learn effective bug fixing and test case synthesis. Section Summary. In this section, we highlight the efficiency of our hybrid attention mechanism for reinforcement learning, RL, scaling, and discuss the unique challenges we faced, such as computational precision mismatches and optimizer sensitivity, which we addressed through targeted solutions. We also detail our diverse data sources for RL training, including mathematical, logical reasoning, competitive programming, and software engineering tasks, ensuring high-quality, verifiable datasets to enhance model performance. Section: General Domain Tasks with Model-Based Feedbacks. In this section, we extend our focus on reinforcement learning, RL, to a broader range of general domain tasks. Since these tasks are not easily verified by rules, we use reward models to provide feedback. Our general RL dataset includes 25,000 complex samples, which we categorize into two types, those with verifiable ground truth answers and those without. The first type mainly consists of STEM and factual problems where answers are objective but can be expressed in various ways, making rule-based checks unreliable. We clean this data similarly to how we handle mathematical reasoning, using our generative reward model, GenRM, as a verifier instead of rule-based methods. To assess the consistency between ground truth answers and model responses, we use a 5-point reward scale. We create a benchmark for human annotated reward models that covers various objective tasks, especially those where rule-based checks fail. We evaluate GenRM's effectiveness by comparing the best responses it selects against established metrics across different benchmarks. This evaluation helps us optimize both the data distribution and the prompt design for GenRM training. For tasks without ground truth answers, we cover a wider range, including instruction following and creative writing. We sample prompts from a large pool using our internal tagging system to maintain a balanced training distribution. Although these queries are open-ended, we aim to pair each with a reference answer for reward model evaluation. We generate responses from various models and assess their quality internally. During RL training, we use a pairwise comparison framework to score model outputs against reference answers, indicating whether the model's response is worse, similar, or better. For instruction following tasks with specific constraints, we apply both rule-based and model-based rewards to evaluate the responses. We build a human annotated benchmark with multiple blind preference judgments to refine our scoring criteria and minimize biases. We also optimize training data through various methods to ensure fairness. Once we have a well-trained GenRM, we use a Swiss round scoring system to identify the best reference answers for RL training. Addressing bias in generative reward models for complex reasoning tasks is crucial. We found that GenRMs often favor longer outputs, which can mislead RL policy optimization by promoting verbosity over quality. To tackle this, we employ standard offline strategies, such as diversifying training data and refining model architectures. However, we discovered that offline evaluations alone do not prevent length bias during RL training. Therefore, we continuously monitor for length bias during training, using specific metrics to detect if the RL policy is producing unnecessarily long outputs for rewards without improving task success. If we identify this behavior, we recalibrate GenRMs immediately to prevent reward exploitation related to output length. We also use RL side techniques like reward shaping and normalization to focus on substantive quality rather than superficial characteristics. Given the diversity of our RL data, a key challenge is training a single policy that performs well on both reasoning-intensive and general domain tasks. To address this, we implement a structured curriculum and dynamic weighting strategy during RL training. We start with reasoning-intensive tasks using rule-based rewards and gradually introduce general domain tasks. This approach allows the model to refine its verifiable skills while enhancing its performance across a variety of tasks, from complex instruction following to open-ended reasoning. This mixed training encourages context-dependent application of reasoning abilities, ensuring the model retains specialized skills while broadening its generalization capabilities. Section Summary. In this section, we extend our reinforcement learning (RL) approach to a variety of general domain tasks, utilizing reward models for feedback due to the challenges of rule-based verification. We categorize our dataset into tasks with and without ground truth answers, employing a generative reward model, GenRM, to evaluate responses and mitigate biases, while implementing a dynamic curriculum to balance training on reasoning-intensive and general tasks. Section: Extending RL Scaling to Longer Thinking. In this section, we extend our reinforcement learning (RL) training to allow for longer output sequences. Initially, we set a limit of 40,000 tokens, but since our hybrid architecture, M1, can handle longer sequences effectively, we increase this limit to 80,000 tokens, creating a new model called MiniMax-M1 to 80K. To train our model efficiently for this longer output, we use our previously trained 40,000 token model to help filter the data. We first check the pass rates on our curated dataset and remove samples that are too easy. We then adjust the data to focus on more challenging problems, like complex math and coding tasks. We also reduce the amount of synthetic reasoning data because it tends to make the training unstable, leading to repetitive outputs that hurt the model's performance. For the length scaling, we adopt a staged approach, starting at 40,000 tokens and gradually increasing to 48,000, 56,000, 64,000, 72,000, and finally 80,000 tokens. This method helps maintain stability during training. We decide when to move to the next length based on specific indicators, such as the model's perplexity and whether the output lengths are nearing the current context limit. These indicators help us ensure that the model is ready for scaling. During this scaling process, we face a significant challenge. The model tends to produce incoherent text in the later stages of training. This issue arises because negative samples grow in length faster than positive samples, leading to an imbalance that affects the model's performance. To tackle this, we implement three main strategies. 1. We detect repetitive patterns and stop early to avoid excessive context usage. 2. We combine sample-level loss with token-level normalization to balance the negative and positive samples. And 3. We lower the gradient clipping threshold to stabilize the generation process. For evaluations, we assess MiniMax-M1 across various domains, including mathematics, coding, software engineering, reasoning, long context understanding, tool use, factuality, and general assistant capabilities. We use specific benchmarks for each area, sampling multiple times to calculate average pass rates. In mathematics, we find that MiniMax-M1 performs well on competitive benchmarks, achieving high scores. In general coding, it matches and even surpasses other models in certain tasks. For reasoning and knowledge, it shows competitive performance against top models. In factuality assessments, it outperforms many open-weight models. In complex scenarios like software engineering and long context understanding, our models achieve strong scores, particularly benefiting from our training environments. They excel in long context tasks, ranking high globally. In tool use scenarios, MiniMax-M1 to 40K outperforms all open-weight models, and MiniMax-M1 to 80K consistently shows improvements across benchmarks, highlighting the advantages of our scaling approach. Section Summary. In this section, we extend our reinforcement learning (RL) training to generate outputs of up to 80K tokens, utilizing a staged window expansion strategy to ensure stability and addressing training instabilities through various solutions. Our evaluations demonstrate that the MiniMax-M1 to 80K model performs competitively across multiple benchmarks in mathematics, coding, reasoning, and long context understanding, often surpassing other leading models in specific tasks. Section: Effect of RL Scaling. In this section, we examine the impact of reinforcement learning, RL, scaling by monitoring performance and response length during training. We present 3 examples from AMI 2024, AMI 2025, and Live Code Bench V5. We notice consistent enhancements in both model performance and response length throughout the training process. Specifically, the average response lengths for AMI and Live Code Bench surpass 20,000 tokens, and the accuracy for AMI 2024 improves significantly from 68% to 80%. Importantly, the strong link between accuracy improvements and longer response lengths highlights the need to extend RL scaling to support more comprehensive reasoning.